The first line of the code imports the warnings module in Python that helps show warning messages when there might be problems during code execution. The second line uses filter warnings with the ignore option, which means it won't show any warnings. This makes sure the code runs without any warning interruptions. This script sets up the required environment by importing essential libraries for training a neural network for asset price prediction. It begins by loading matplotlib to display charts within the notebook. Then it loads additional libraries needed for data handling, plotting, statistics, and preprocessing, such as OS, Sys, NumPy, Pandas, and Seaborn. For model construction, sequential indents are imported from TensorFlow.keras. These components are crucial for data preparation, visualization, and creating the neural network. The code sets GPU devices as the list of GPUs, then checks if any are available. If a GPU is found, it prints using GPU, and if not, it says using CPU. This code adds a parent directory to the Python search path so it can access a custom module named utils. From utils, it imports the multiple time series CV and format time functions. These functions are probably specialized for the project's goals. The code is preparing to use a deep neural network to forecast asset prices, although the code for the data and network structure isn't shown here. This code starts by initializing a consistent random number sequence, so you get the same results every time it's run. It then chooses a clean, grid-style look for the graph. After that, it uses a special function pd.indexSlice to easily work with complex data tables, getting them ready for use in training a neural network. This code specifies where to store and find the data for training a neural network to predict stock returns. It uses an H5 file, which means the data is saved in a format good for handling big data sets. Setting the path helps the neural network quickly find and use the data, which is crucial for successful training and creating an accurate model. This code makes a results path using the path class. It checks if results path is there, and if not, it makes the folder. Inside, it makes a checkpoint path to save training logs for the DeepNN model. This code loads the data.h5 file into model data, drops any incomplete rows, and sorts the data. It's prepared for a machine learning model to predict asset prices. The code uses the info method on the data object to summarize the dataset. This includes the names of columns, the total number of rows, and the type of data in each column. By setting show counts to true, it also displays the number of non-missing values per column. This summary helps identify which columns have missing data and how to prepare the dataset for a deep neural network model. It's a tool for getting a quick overview and planning data processing steps. The code assigns the outcomes variable a list of column names from the data object that include FWD. It uses a filter function to pick these columns and turns them into a list. The code sets up two variables. Lookahead gets the number 1, and outcome is assigned a string that includes lookahead's value with 2 digits. Padded with a 0 if it's a single digit, e.g. R01FWD if lookahead is 1. In the context of predicting future asset prices with a deep learning model, lookahead represents how far ahead in time the prediction is, here 1 time step ahead. The outcome string is used as a label in the model, which learns to forecast the next time step's asset prices based on current data. The model's goal is to make predictions that closely match the real results. This code prepares data for testing a deep neural network that predicts asset price movement. The first step is to create a variable, xCV, which holds a subset of the data selected by the lock method. It includes rows with an index higher than the IDX variable's value but before or during 2017, and it keeps all columns except those listed in outcomes. The second step sets up another variable, yCV, with the lock method to hold the target results for the validation set. These steps result in 2 datasets, one for model validation and one with the results expected, based on specific index ranges and columns from the original data. The code gets the unique symbol entries from the xCV dataset to count how many different assets the neural network will analyze for predicting price returns. This function analyzes a dataset and prints out key details like the number of entries, each column's data type, and the total memory used. With the null counts option, it can also show missing values. This helps identify issues like incomplete data or incorrect data types before using the dataset to train a deep neural network, ensuring that the data is properly prepared for effective training. It's a crucial step for understanding and readying a dataset for neural network training. This code defines a make-model function that creates a neural network using the keras library. It takes a list of the number of neurons for each layer, an activation function, and a dropout rate to combat overfitting. It starts by creating an empty model and then adds layers based on the given list. The first layer is special because it needs the input size. For the rest of the layers, it adds them with the specified activation function and a dropout layer after each. An output layer is added at the end. The model uses the Atom optimizer and is set up to minimize mean-squared error. Once compiled, the model is ready to be used and is returned by the function. The code sets up 3 variables for training a deep neural network to forecast financial asset prices. N splits is at 12, meaning the dataset will be split into 12 parts for cross-validation. Train period length is 1008 days, calculated as 21 days per month for 4 years. Test period length is 63 days, equating to 21 days for 3 months. These settings will help the network learn from the data and test its predictions. This code sets up a tool called Multiple Time Series CV that helps improve a neural network's ability to forecast financial returns. It does this by dividing the data into several chunks to repeatedly train and test the model, ensuring it works well on new data. This tool is tailored for sequences of data over time, making sure training and testing don't mix. It lets you choose how many divisions, N splits, how long each training and testing phase should be, train period length, and test period length, and how far into the future the network should predict look ahead. These settings help prevent the model from being too tailored to the training data alone. This code sets up configurations for a deep learning model to forecast financial returns. It starts with a list of increasing layer sizes, meaning each layer has more nodes to add complexity. The second part lists activation functions, which decide a neuron's output. The third part lists dropout rates, which help avoid overfitting by dropping some nodes randomly during training. The code combines these settings for training the model. This code generates a shuffled list of different settings for dense layers, activation functions, and dropout rates for training a deep neural network to forecast financial asset returns. It first combines every possible setting from the 3 groups using the product function, then np.random.shuffle mixes up these combinations to avoid bias due to their initial sequence. The randomized list is then ready for use in optimizing the model, aiming to enhance the prediction quality. The code measures how many sets of parameters, param grid size, the model needs to try to optimize its predictions of asset price returns. This size dictates the total training cycle's epochs required. The getTrainValidData function splits data into training and validation sets using given indices. It takes 4 inputs: features X, targets Y, training indices trainIDX, and validation indices testIDX. Using iLock, it chooses rows for training and validation from X and Y according to the indices provided. The resulting subsets, training features XTrain, training targets YTrain, validation features XVal, and validation targets YVal, are then returned. This function prepares the data needed to train a model for predicting asset price returns. This code sets up a list called params with 3 settings for training a model that forecasts financial returns. Dense layers is how many connected layers are in the model. Dropout is the rate at which data is excluded to avoid overfitting. And batch size is the number of data points trained at once. Tweaking these settings helps improve the model's predictions. This code trains a deep neural network to forecast asset price returns. It loads data from a scores group in an IC by day file found at results path. The data is stored in a variable named IC, and its details are shown using info. Finally, the activation column is removed from the IC data. This code counts how many times items appear in categories of a given dataset and shows the totals. This helps spot patterns in the data, which can be useful for making predictions, like forecasting changes in asset prices. This code transforms a wide-formatted data frame named IC into a long format using the pd.melt function. It keeps certain columns ID vars, params plus fold as identifiers, and renames the variable and value columns to epoch and IC respectively. In the long format, each observation is split into multiple rows, each showing a different IC value for each epoch. Finally, the iclong.info function gives details about this new long-form data frame, like the total row and column count, as well as the data types. This code organizes the iclong data by epoch and fold, computes the average of the IC column, and stores it in a new data frame called IC. It then reverts the data frame's index to its original arrangement, providing a summarized view of the data for simpler analysis of trends and patterns. The code loads Seaborn, a graphing library with the alias SNS to create a line chart. It uses the relplot function to plot epoch against IC, categorizing data by dense layers and dropout from the IC-long data frame, but only where dropout is above 0. A horizontal dashed line at y=0 is added to the plot for reference using the map function. Lastly, the plot is saved as a high-quality 300 dpi image for later use or presentation. This plot helps to analyze how dense layers and dropout affect the IC metric over epochs. This code changes commas to hyphens and removes parentheses in the dense layers column of a data frame. Then it reshapes the data frame into a long format and adjusts the epoch column to a 2-digit number format. Next, it sorts the data and performs one-hot encoding, excluding the first dummy variable. The column names are updated to just show the epoch number. Finally, the data is used to fit an OLS regression model, predicting asset returns with the IC column as the target and other columns as predictors. This code is training a neural network to predict asset prices. It begins by removing the fold column from the IC variable since it's not needed for predictions. After that, the run-ols function is used to train the neural network with the ordinary least squares method. When the training is complete, the model will be ready to predict future asset prices. This code displays a brief overview of a deep learning model, showing its layers, the number of parameters in them, and their output sizes, which helps to grasp the model's design and pinpoint any possible problems or areas to enhance. The code generates a bar chart to show how different network designs and training settings affect a deep neural network's performance on new data. Initially, it sets up the plot space. It then computes the confidence interval from the trained model and calculates error bars. Model parameters are organized into a table, excluding dates and constants. Afterward, the bar chart is drawn, labeled, and enhanced with coefficient scatter points and notes about each training parameter's influence. The finished chart is then styled and saved as an image. This code defines a function getBestParams with a default parameter n set to 5. The function's purpose is to select the best settings for a neural network using a dataset's median daily performance IC. It does so by evaluating a set of parameters: dense layers, activation, dropout, and batch size. Here's a summary of the steps. 1. It reads the content of scores.h5 into variable IC and removes the fold column. It extracts unique dates and picks the first 504-2421 as the training period. 3. It filters IC to include only training date data. 4. It calculates median IC values for each combination of parameters. 5. The data is then reshaped and sorted to identify the best performing parameter combinations. 6. The top n combinations are converted to a dictionary list, excluding their IC scores, to be returned from the function. The function ultimately returns a list of dictionaries that represents the optimal settings for the neural network based on the data from the training period. The code uses a simple neural network to predict asset price returns. It sets up the network structure and training process with user-defined settings like number of layers, activation function, dropout rate, batch size, and number of epochs. The process involves 1. Reading data from a file, cleaning it by removing missing values, and organizing it by index. 2. Extracting target variables, those with FWD in the name for prediction. 3. Using data before 2017 for cross-validation CV, separating input features XCV from targets YCV, specifically the R01 FUD column. 4. Scaling the features with standard scaler for normalization. 5. Splitting the data into training and validation sets and scaling the validation set. 6. Building and training the neural network model based on the provided parameters. 7. Loading previously saved model weights, predicting on validation data, and storing results. 8. Combining all predictions into a single data frame to output the final predictions. This code trains a neural network to forecast financial asset returns. It first finds the optimal settings with the getBestParams function. Following that, it initializes an empty predictions list. It loops over each set of optimal parameters, generates predictions using them, and stores these predictions as data frames in the list. After making all predictions, the list is combined into one table and saved in HDF format. Lastly, it prints out details about the predictions for review.